Hello and welcome. Today I'm going to explain molecular absorption and emission. So a few videos ago I talked about single atoms and the electronic absorption between electronic levels in single electron atoms. And single atoms can only be excited electronically. Single atoms do not rotate and they do not vibrate. So single atoms only get electronically excited. And the energy to be electronically excited is E sub n, or let's say the final to the initial state, is some constant times the charge of the nucleus squared times 1 over the final quantum number squared minus 1 over the initial quantum number squared. And that has to, if that equals the frequency of light you're shooting times some constant, then you're going to electronically excite the atom. And this is for 1 electron atoms. Now, multiple electronic atoms are much more complicated, and I'm not going to go into that in this video. Yet more complicated is collections of atoms. Collections of atoms that are connected. Another name for those are molecules. And molecules can rotate and they can vibrate. So let's take the simplest collection of atoms. Let's say we got an atom here and an atom here. Well, those atoms are binded together by electrons. You can imagine this like a dumbbell, except the middle of the dumbbell is stretchy. So imagine 2 balls connected by a spring. That's a better analogy. So these 2 balls can vibrate back and forth, and they can also rotate in space. If you only have a single atom, it doesn't, you could visualize it rotating, unless the atom is uniform all the way around, then it's going to look the same no matter what direction you're looking at it from. So we say it doesn't rotate. But if this is rotating, and you look at it from different angles, it is going to look different. So this is the simplest molecule we can have, and it's a diatomic molecule. It means 2 atoms. And we're going to use this as our picture throughout the rest of this video. So, in quantum mechanics, things only have discrete energy levels. That goes for electronic energy levels, vibrational energy levels, and rotational energy levels. So the highest energy levels are electronic levels. The next highest is vibration levels. And so vibrational levels are smaller in energy than electronic, and rotational energy levels are smaller than vibrationals. So To get a better visualization of the dynamics at play, let us draw the following figure. So we draw a plot, and on this vertical axis is the energy, and on this horizontal axis is the distance, which I'll call r, between these two atoms. So this would be the distance r, and r is able to vary because the atoms are vibrating. Sometimes the atoms are close together, and at a different time they may be further apart. And depending on how far they are apart, that's going to affect the energy of the whole molecule. So we can have electronic energy levels, like I said, and those are shaped something like this. And this would be the electronic energy level 0. Okay, this is the furthest one down, the one lowest in energy. It's arbitrary where we put it on this e-axis. Now we can have an excited electronic energy level, which would be this one here. So this is electronic energy level 1. Now vibrational levels, the spacing between them is smaller than electronic energy levels. So vibrational energy levels lie within these electronic levels. Something like so. So these lines here I'm drawing are the vibration energy levels. Okay? So this one right here would be called, this is vibrational level 0 within electronic energy level 0. And similarly, this line right here would be vibrational level 1 within electronic energy level 0. This one right here is vibrational level 0 within electronic energy level 1. Makes sense, right? And the spacing between these vibrational levels are more or less the same, unless you start to get real high up. The further up you go, the more spacely close they are. But near the bottom, they're pretty much, the distance from this line to this line is the same as the distance from this line to this line. But that's the distance from this line to this line is not necessarily the same as it is from this line to this line. This point right here is the smallest point in energy that the molecule can achieve. This point here. And the distance at which the atoms are apart at that level, I'll denote R sub E, and R sub E is the bond length, or the E really stands for equilibrium. So you might see it as the equilibrium bond distance, which just means it's the molecule most of the time is going to be located, well, it'll be in the 0th vibrational level. I should mention that the vibrational level can't lie at the very bottom of this well. It lies a little bit above it. Now, let us zoom in to this here, okay? So imagine us zooming in. So we'll draw our axis again. This was energy. This was distance between the atoms. Remember, we're only working with 2 atoms. This right here, I zoomed in. This is the electronic energy level 0. And then we have our vibrational levels. Let's put the lowest one down there, next lowest one there, next lowest one there. You can see the energy spacing between them is the same. Now, within these vibrational levels, we have rotational levels, which I'll denote by these dotted lines here. So this one, right here, vibrational levels can be located on the first, so the rotational level can be located on the vibrational level. Unlike the vibrational level can't lie way down here. That might be clearer when I write an equation down. So this would be called rotational energy level 1. Right? 0 would be down here. This would be 0. So this is rotational energy level 1 within vibrational energy level 0 within electronic energy level 0. Okay? And this is our equilibrium bond distance there. Now, the rotational energy levels, unlike the vibrational ones, increase in spacing as you go up. So down here near the bottom, the rotational energy levels are very close together. And then you go up one more, it's a little bit more space than it was before. And then you go up one more yet, and the spaces starts to get bigger, and then bigger and bigger and bigger. So, let's write down some equations now that we have somewhat of a visual picture in our heads. Let me draw the energy well again, just so we remember what it looks like. So I'll just draw the bottom one. These are the vibrational levels. The rotational energy levels are in there. They're just really small, so you can't really see them that well. Now, this well here could be fat or it could be skinny, right? And so I'm going to use this word called curvature, which means how fast does this thing, curve. So something with a very high curvature, would look like that. Something with a very low curvature would look like that. And now, the curvature of the well determines this constant called K. So I'll say determines K, which is called the force constant, or the stiffness of the spring that connects the 2 atoms. Remember, we had 2 atoms, they're connected by a spring. So the K is a measure of the stiffness of the spring. So the greater the K value, the more curved this thing is going to look. It's going to look more like this. This has a high K value, this has a low K value. So now, to determine the vibrational energy levels, use the following formula. H bar omega n plus 1/2. And h bar is Planck's constant divided by 2 pi. Omega is the angular frequency, which is related to frequency I've been talking about, just differs by a factor of 2 pi. And omega equals 2 pi nu, but also equals this force constant K divided by this thing mu, which is the reduced mass. So mu equals reduced mass. And the reduced mass is equal to the mass of the first atom times the mass of the second atom divided by the mass of the first atom plus the mass of the second atom. And if you have 3, you can probably guess how it's extended. You'd have m1 times m2 times m3 divided by m1 plus m2 plus m3 would be the reduced mass for a 3 atom molecule. But we're just working with 2 atoms here to keep things simple. So we can also write this energy up here as equal to h omega. So what I want to do here is substitute for omega. So h bar k over mu n plus a half. Now if we take the difference between one vibrational energy level and the next, we would get h bar omega, or h bar square root k over mu. And you can see that's a constant for as long as you have the same molecule. So that's why I said earlier that the spacing between the vibrational levels was constant, because this formula tells us that. And K is different for different molecules, and so is mu. Okay, now let's talk about the rotational energy levels. So the rotational energy levels, E sub rot, are... Oh, I forgot to mention up here that this n is called the vibrational quantum number, and n has to equal either, it can be 0, or it can be 1, or 2, or 3, and so on and so forth. And the same thing with these, I'm about to write J. So J is the rotational quantum number, and it can also be 0, 1, 2, 3, but nothing in between. And now this is the formula for the rotational energy levels. And remember, Re is the bond length, and mu is this same mu for the reduced mass, and J is the rotational quantum number, which can be 0, 1, 2, 3, so on and so forth. Now if you take the difference between the rotational energy levels, you can try it yourself. You just add 1 to J, and then you minus an energy where you didn't have J. So I'm taking 2 rotational energy levels that are next to each other. I'm not skipping one, is what I'm doing. So you get h bar squared over mu times Re squared J plus 1. So what this tells us is that the higher your rotational energy, well, the spacing to the next rotational energy is going to be greater. So you start with, let's say, the smallest rotational energy level down here. Well, and then let's say your next one's, so this would be J equals 0. Here, J equals 1. And then the distance is going to get a little bit bigger than this distance. So maybe like right there. This would be J equals 2. And then the next space is going to be larger than this space. So maybe something like that. J equals 3. J equals 4. J equals 5. And then I think you see the pattern. Okay, so that's a little bit on molecular absorption and emission. In future videos, I'm going to go into a lot more detail on how this works. This is just a very simple summary of a lot more complicated, I guess you could say, details. So thanks for watching and have a good day.